Assalamu alaikum. Welcome to the next class. In this class, we'll be discussing about the different methods of equalizing the potential across the different units of a suspension insulator. So the first one method is the selection of M. Actually, in this case, we are using the higher value of M, and grading of units, we are using different units of different capacitances, and in other case, we are using a guarding known as static shielding. The first one is the selection of M. In this case, we may use the capacitances or we may use the disc insulators which will provide a higher value of the capacitance as compared to the capacitance of the metal parts of the insulator to the ground. So this can be achieved by using the material of the insulators which have a higher dielectric strength, or this can also be achieved by increasing the distance of the insulator string from the tower structure. So in that case, if we do that, the cross arm length will be higher and the supporting structures will be taller, which results in an uneconomical uh, system. So if we go beyond that certain value, we may be having an uneconomical system. Practically, M can be having a maximum value of 10. So beyond that, it will not be good to have. Even if we can have M is equal to 10, we can still not be sure that we can neglect the capacitance of metal to ground, but we can minimize it. But still, it will not make this voltage distribution uniform. The second one is the grading of units. As we already know that the current flowing through this part, that is the insulator which is close to the power conductor, is maximum, and the current flowing through this insulator disc which is close to the tower structure is minimum. So we can exactly make the potential distribution same. Even if we have the leakage currents, we can have different types of or different insulator disc having different capacitances. The capacitance over here should be minimum so that the reactance is highest, which makes the multiplication of current and reactance equal to the other parts, and here the capacitance should be highest and reactance should be minimum so that the maximum current and minimum reactance multiplication will make them equal. So we know that this unequal voltage distribution is due to the leakage current from insulator pin to the tower structure, that is these currents. So these currents cannot be eliminated. What is the other possibility? That I have just told you, that we can use a different capacity discs such that a product of their capacitive reactances, that is this and this, multiplication of I and XC1, and the current flowing through the respective units is the same. So that product should be same. That means we have the unit having the highest capacitive reactance at this and lowest capacitance, and we have a unit having the lowest capacitive reactance at this place and highest capacitance. So this requires the unit nearest to cross arm should have the minimum capacitance, maximum capacitive reactance, and as we go towards the power current, the capacitance should increase. By this grading, it can be shown that complete equality of voltage can be obtained. So if we do this, so voltage across each unit will be same. So let us try to use this and try to derive a single formula or single equation in which we can calculate different capacitance values of different units. Here the ground capacitance is C are equal, but the values of mutual capacitance are different, and that depends upon the multiplication of the current and the capacitance. Since we assume that equal voltage drop across the various units, that means the voltage across this unit will be V, the voltage across this unit will be the small v, the voltage across this will be V, the voltage across this will be V. So this is the nth capacitance, this is the nth ground capacitance. From here to here, the total voltage will be N times V. That means N times V voltage will appear across this capacitance. So In plus 1, that is this, we are using KCL at this point. In plus 1 will be equal to In plus ICN, that's given over here. So In plus 1, it will be equal to voltage multiplied by its capacitive admittance. Voltage is V, capacitive admittance is Cn plus 1 into omega. That is this, V into omega into Cn plus 1. So what will be the current In in terms of Cn and V? It will be equal to V into Cn into omega. That is V omega Cn. Similarly, the current flowing through this, it will be equal to total voltage across this string, that is NV multiplied by omega C, because we are assuming the capacitance of these strings is equal to C. So uh, eliminating this omega into V, omega V and omega V. So we are left with Cn plus 1 is equal to Cn plus NC. So if we know the capacitance value of this and this, we can calculate the capacitance of any unit in terms of these two values. So you can see C2, that is when n is equal to 1. When n is equal to 1 at this point, then C2 will be equal to C1, that will be this C1 plus C, that will be these two. And C3, that will be equal to C2 plus 1, that is C2 plus 2C, because C2 was equal to C1 plus C, that means then C2 will be equal to, C3 will be equal to this C1 plus 3C. Similarly, you can calculate any value of the capacitance from going this to this in terms of this C1 and in terms of this C. From this, it is clear that the capacitance of one unit is fixed. The capacitance of other unit can be found for the equal distribution of voltage across the units of the string. That fixed capacitance is the C1. This means that in order to carry out the unit grading, units of different capacities are to be required. This requires a large stocks of different size units, which is uneconomical and impractical. So that means we are not practically doing it. So what we practically do, we are doing this static shielding and use of guarding. In case of a unit grading, we used units of different capacities so that the flow of current through the respective units produce equal voltage drop. So we have discussed this just before. But in static shielding, the idea is to cancel exactly the pin to tower charging current so that the same current flows through the units of identical capacities to produce an equal voltage drop across each unit. In this case, we are using this identical units and we are trying to find out the method in which these charging currents or leakage currents are cancelled out by these currents. When this happens, you can see same current will flow throughout the string. Since they are identical, their capacitance will be same, their capacitive reactance will be same, and hence their voltage drop will be same. That means potential distribution will be uniform. So in this method, a guard ring or a grading ring is connected around the power conductor such that this surrounds the bottom unit. So it surrounds like this the bottom unit. Since identical units are being used, their capacities are equal. Their capacities will be equal. Similarly, the ground capacitance are equal. This C will also be equal. The design of the ring should be such that this gives rise to a capacities which will cancel exactly the charging current in a particular section, such that you can see for every this In plus 1 should be equal to this In when these currents are equal. That means this is equal to this, and ICN will be equal to ICN dash. Since ICN across this capacitor from this point to this point, this voltage appears, and we are assuming that all the voltages, it is the uniform voltage distribution. That means the voltage across this capacitance is V, this insulator disk is V, this insulator disk is small v, this V. That means from this point to this point, the total voltage will be NV. That is this. So the current ICN will be equal to NV into omega C. Similarly, the voltage across this point and this point will be, you can see the voltage will be the power conductor voltage. That will be total voltage minus this voltage. The total voltage will be V minus this voltage will be NV and omega Cn. we're assuming the value of Cn over here, the value of this capacitance is Cn, where V is the operating voltage and Cn is the capacitance between the guard ring and the pin of the nth unit. Pin of the nth unit is this. So let V is equal to kV, where K is the number of units used. When K is the number of units used, this is V, this is V, this is V, this is V, total are K. The total voltage will be kV, and we're assuming total voltage to be V, that means kV is equal to V. So by putting here kV and taking V as common, it will be equal to K minus N into V omega C. So V omega and V omega will cancel out, it remains Kc, Nc is equal to K minus N into Cn. So Cn will be equal to N divided by K minus N into C. In this way, we can calculate the value of the capacitance of the guard ring to the pin of the insulator in terms of the capacitance of the pin to ground. In order to obtain the perfect equal distribution of the voltage, the capacitance of the guard ring with respect to the pins of the insulator can be given or can be calculated by this expression. In practice, it is very difficult to achieve this condition because we don't know where to keep the guard ring to exactly cancel out the leakage currents. What we do then? It has been found that for a 14 unit string, the voltage across the bottom unit without the guard ring is 18.3% of the operating voltage, and with guard ring it was found to be 11.8%, which is of the great improvement. You can see 14%, 14 units, sorry. So normally it should be that everyone should get around 7.14% voltage across each unit, but without guarding it was 18.3%, but with guarding it is 11.8%. So what I mean to say is, in this case we are not perfectly designing it in such a way so that we get capacitance from this formula. We just put the guarding in this way without actually calculating the actual values, and then you will see there is a slight improvement in the voltage distribution. You can see from here to here it should have been 7, but it is 11. It has improved from 18 to 11. So it has not exactly matched from 18 to 7.14%, which is very difficult to achieve. So practically grading ring serves two purposes: equalizing the voltage drop across the two units, not equalizing, but we can say it makes improving the voltage distribution. It is improving. When used with the arcing horn, which is fixed at the top of the string, it protects the insulator string from flashover when an overvoltage under the normal or abnormal condition appears between the tower structure and the power conductor. So we are using these arcing horn actually to safeguard this insulator string. Whenever the higher voltage surge appears across the conductor, there is a voltage flashover between arcing horn and this guard ring. In this case, it will protect this insulator string. The combination of the two provides path through the air medium to the discharge energy contained in abnormal voltage, and thus insulator string is saved. If these two were not present there, it would have the insulator string would have provided the path for this flashover voltage to pass through, and energy have been discharged through the insulator string, and insulator string may have got a damage. But it provides the combination of this arcing horn and guard ring provides the path through the air. Air becomes conducting, and all the energy is dissipated through that air, and in this case insulator string is saved. So let us try to do some numericals to understand it better. Determine the maximum voltage that a string of suspension insulator of this figure can withstand if the maximum voltage per unit is 17.5 kilovolt. And we know that this is the maximum voltage that should appear across an insulator. So when we need to first understand, since we have three insulator strings over here, so we need to understand first which insulator should be fixed to have this much of the rated voltage. So in this case you will see that since this is maximum voltage that should appear across the string, that means we need to design or we need to find out the voltage so that the voltage across the string, that is this string should be equal to 17.5 kV. That means this E3, since this is the maximum voltage, should be equal to 17.5 kilovolt. If we assume this E1 to be equal to 17.5 kV, you will see that E2 will be still greater than this and E3 will be still greater than this. And when we apply such voltage across this, their voltages will be greater than their normal operating voltage. These two may get damaged. So in that case, we have to design in such a way, we have to make calculate the operating voltage in such a way so that this maximum voltage should appear across this. That means E3 should be equal to 17.5 kV. Let the voltage across the various units be denoted, that's E1, E2 and E3 as shown, so that E1 plus E2 plus E3 is equal to E, where E is the desired withstand voltage of the string. Applying Kirchhoff's current law at point A, that means I2 is equal to I1 plus IA. So here it is given that C dash is equal to C by 8, or we can say if this is C, this will be 8C. So M is equal to 8 here. So the voltage across here is also equal to E1. It will be E1 omega C, that is this, and E1 omega, this C dash is C by 8. C by 8. Omega C will cancel out. So it will be equal to, and this I2 will be equal to E2 into omega C. E2 into omega C. So from here, when we equate them, E2 is equal to 9 by 8 E1. Similarly, at point B, I3 is equal to I2 plus IB. By the similar calculation, you will get that E3 is equal to 89 by 64 by E1. But E3 should be equal to the 17.5 kV, the maximum voltage that it should bear. So by putting this, it can be seen that the voltage across the line unit, that is the power conductor, is maximum. That means E3 should be equal to 89 by 64 into E1, that is equal to 17.5 kV. That means E1 should be equal to 12.58 kV and E2 should be equal to 14.15 kV. You can see that E3 is this, E2 is this, and E1 is this. If you keep this E1 to be equal to 17.5, you will see that E3 and E2 will be higher, and they will, in the normal operating condition, they will get damaged. The total voltage summation of three voltage will be equal to 44.23 kilovolt. In this way, when we apply this much of the voltage, in that case you will see the voltage E1 will be given by this voltage, E2 will be given by this, and E3 will be given by this, and in this case there will be no string that will get damaged. Now one more numerical. A string of 8 suspension insulators is to be fitted with a grading ring. If the pin to earth capacitance are all equal to C, find the value of line to pin capacitance. That would give the uniform voltage distribution over the string. That means we need to find out these capacitance C1 to C7. So from this figure, IA is equal to capital IA, IB is equal to capital IB, and so on up to this. So E1 is equal to E2 is equal to E3 is equal to E8 from this to this, because we are assuming that when guarding is used and proper design of these capacitance are to be calculated, their voltage will be same. So I is equal to omega C E by 8, and this is the case we're assuming a total voltage of E appearing across this. That means E1 will be equal to E by 8, E2 will be equal to E by 8. Similarly, all the voltages. So I is equal to omega C E by 8, that is this, because this will also have a voltage across it as E by 8. And IA is equal to C1 omega 7 E by 8, because the voltage across this will be the total voltage that is appearing across this conductor with respect to ground minus this voltage. That means E minus E by 8, that will be 7 E by 8. So total, when we compare these two equations, C1 will be equal to C by 7. By doing the same calculation, IB is equal to capital IB. IB is equal to capital IB, where IB is equal to twice E by 8, small IB, because here we have twice E by 8 voltage will appear across this, and the voltage across this will be equal to 6 E by 8. So when we compare these two, you will get C2 is equal to C by 3. By approaching similarly from this point to this point, you will get C3 is equal to 3C by 5, C4 is equal to C, C5 is equal to 5C by 3, C6 is equal to 3C, and C7 is equal to 7C respectively. This can be also done by using this formula. The equation can also be used to calculate all the voltages from n is equal to 1 to 7, where k is equal to total number of string in this, that is equal to 8. You will see that when n is equal to 1, k is equal to 8, it will be equal to 1 divided by 1 divided by 8 minus 1, that is C by 7. You can see that we have calculated C1 is equal to C by 7. Similarly, when n is equal to 2, this will do 2 divided by 8 minus 2, that is 2 divided by 6, that is C by 3. You can see we have calculated C by 3 already. And for n is equal to 3, it will be 3 by 5 into C. That is over here, 3 by 5. That is 5 by 3C. So by using this formula, you can also calculate the same. Now, one more numerical. This is very important because it is relating to the practical way of using the guard ring. Determine the voltage across each disc of suspension insulator as percentage of the line voltage to earth. The self and the capacitance to ground of each disc is C and 0.2C respectively. That means this is C and this is 0.2C. The capacitance between the link pin and the guard ring is 0.1C. That is given as 0.1C. This is the first case. Second one, if the capacitance of the line of the lower link pin wire increased to 0.3C, that means this, if it is increased to 0.3C by means of a guard ring. Determine the redistribution of the voltage, also determine the string efficiency in each case. So we need to find out the voltage across these three units and we need to find out the string efficiency. Let us first try to do the part A when we have this is equal to 0.1C, this is equal to 0.1C. So in that case, let us assume that we have voltage over here E1, we have E2 and we have E3. So in this case, this is the current I2 plus this, let us say this is IX. I2 plus IX is equal to IA plus I1. That is the KVL written at node A. So it will be equal to E2 omega C, that is this E2 omega C, and this voltage will be equal to E2 plus E3. E2 plus E3 into omega into 0.1C, that is this, minus it has taken them to the left side. This is I1. I1 is equal to E1 omega C, E1 omega C, and IA is equal to 0.2 E1 omega C, 0.2 E1 omega C, and putting them to 0. Now collecting E1 and E2, collecting E1, E2, E3 separately, it will be 1.2 E1. You can see we have E1 over here, E1 over here, that is minus 1.2 E1, and then E2 is here 0.1, E2 is here 1, that is 1.1 E1, and 0.1 E3, that is here. So we get this equation at this node. Similarly, for this case, you will see that this I3 plus IY, let us say this current is IY, is equal to IB plus I2, or I3 plus IY minus IB minus I2 is equal to 0. Putting different values, we get this equation, that is 0.2 E1 plus 1.2 E2 minus 1.1 E3 is equal to 0. Now we have two equations. One is this equation, another is this equation. There are three unknowns with two equations. We divide both of them by E3 and written them as. When we divide both of them, let us say we divide here by E3, it will be equal to 1.2 E1 by E3 minus 1.1 E2 by E3 minus 0.1, and then I will multiply it by 10. It will be 12 E1 by E3 minus 11 E2 by E3 minus 1 is equal to 0. Similarly, for this case, it will be equal to twice E1 by E3 plus 12 E2 by E3 minus 11 is equal to 0. Then I will take E1 by E3 is equal to X and E2 by E3 is equal to Y. Then the equation, first equation, that is this, it becomes 12X minus 11Y is equal to 1. That is this. Similarly, this will become twice X plus 12Y is equal to 11. That is this. After that, it is very simple to calculate for X and Y. After solving for X and Y, Y comes out to be 65 by 83, that is 0.783, that is E2 by E3, and X is equal to 0.801, that is E1 by E3. So E2 is equal to, in terms of E3, 0.783 E3, and E1 is equal to 0.801 E3. E is equal to E1 plus E2 plus E3, that is equal to 0.801 E3 plus 0.783 E3 plus E3. It comes out to be 2.584 E3. So E3 will be equal to this E divided by this weight. So E3 will be equal to E divided by this quantity into 100. That comes out to be 38.70% of E. So E2 is equal to 0.783. You can see from here E2 is equal to 0.873 into E3, but E3 is equal to this value 0.387. So when you multiply this, it comes out 38.30.3%. Similarly, E1 will be equal to 31%. So the efficiency, the string efficiency will be equal to 1 divided by 3 times the voltage across E3. That is E3 is 38.7.387. 0.37 into 100, that's 86.1%. So this was the case when we have assumed that we have the guard ring has a capacitance of 0.1. Let us now increase this to 0.3, and the equation over here will not be modified to be same, but equation here will be now modified. So if the capacitance blind will be 0.3, the equation at the A is unchanged, whereas the B now becomes, the equation at B becomes 0.2 E1, 0.2 E1, 1.2 E2, and this becomes 1.3, because you can see over here we have used 0.1 at this point only, because E3 into 0.1. Now it comes out to be E3 into 0.3 omega C. This is the only case where we are using this. When this comes, that means E3 will be increased by 0.2. Here it is 1.1. In the new equation it will be 1.3. Rest will be same. You can see over here. So our equation will be now, this will be twice x plus 12y minus is equal to 13. Earlier it was 11. So when we solve this, we get y is equal to 0.9277 and x is equal to 0.9337. That means E1 by E3 is equal to this term, that is this, and E2 by E3 is equal to this term. That means E1 is equal to 0.9337 E3 and E2 is equal to 0.9277 E3. So total voltage, the summation of three voltage will be equal to 0.9337 E3 plus 0.9277 E3 plus E3. So then E3 will be equal to, when we calculate its total sum, 0.9, 0.9, 1.8, 2.8, it will be 2.85 something, and then E3 will be E divided by 2.85, it comes out to be 34.94%. So E2 will be equal to 32.42% and E1 is equal to 32.63%. You can see that their voltage distribution is almost same, and the percentage string efficiency will be equal to 1 divided by 3 into this part is 0.3494. 0.3494, it comes out to be 95.4%. So practically this guard ring is used like this, where it can slightly improve it, but it will never make it equal to 100%. We have perhaps done this thing in the lab also, where we use only one capacitor. In that case practically we are using in the same manner. Okay, thank you. I am stopping.